Next speaker is Dr. Hadi Hajibeygi from TU Delft. He's going to be talking about energy storage in salt caverns.
Good morning, everyone. It's my true pleasure to be in this beautiful city and this event. I've learned already a lot, and thank you very much for waking up again the next day early in the morning, despite the last night late evening party that we had. Gala dinner, I guess. So today I'm going to talk about energy storage in salt caverns. And we do in our chair in subsurface storage and multi-scale modeling various type of research, but for this event I've selected the salt cavern, in part also that my friend and colleague Sebastian will cover the rest of the porous rocks and heterogeneities as well. And the work is presented by me like many other chairs, if not all, and the real work has been done by our talented students who are actually sitting some here. Naomi is sitting there, and if you have hard questions, actually she's the best to ask. So why salt and why salt caverns? From your kitchen table, the taste of this salt, think, and how is it relevant to a warm bath in Rocky Mountains, if you're so fortunate to have one. The story comes with all the factors that are related to energy, and all of us, 8.2 billion people, we all live in this planet Earth. Soon, by the end of the century, we will be about 10 billion people. And that increase of access to resources, utilities, and welfare, and all has been thanks to the factor, to the term that we call as energy. Energy has been able to be scaled up, and so has allowed us live prosperous. But this has not come with no side effect. As a consequence, very much coinciding on the same plot of energy scale up, the emission of CO2 has actually increased a lot, significantly compared to the past centuries. The world is in transition. We are not yet witnessing a stable equilibrium state, so that's what we call as transition. We don't know what the consequences of even today's emitted carbon will be in long term. And so there are a lot of opportunities to look into to say, is it possible to find a way to fix the problem and move to the right direction? Sustainability does not mean just to be clean, but also that we can live and create welfare and prosperity. And that's not a trivial question to answer. And so if there is one way that this can happen, we are supposed, for our responsibility to the next generation, to find that one way. There are many ways that this cannot work. So what can we do? Go to low carbon energy systems. And there, hydrogen comes. Hydrogen has been seen as perhaps a hope for that it might be indeed the missing link of the scalable low carbon energy system. A hope. Maybe it is it. Maybe that's it. And that's why we work on it. To say, is it possible that we solve this scalability of low carbon energy systems with that energy carrier? And for that to happen, obviously, storage would be extremely important among transportation production. And hydrogen, because it's gas and we know what to do with gas, we can actually try to find ways to store it at larger scales. Surface facilities have been used for decades in space agencies, and they are still crucial. Beyond that, salt caverns have been also used for different purposes for energy storage, and obviously porous reservoirs, which allow you go towards several terawatt-hour of energy storage. Today, I am focusing on salt caverns and not others. And how are they relevant and why they are actually already crucial to what we have already today. So they have been always as a backbone of energy system for decades. Salt. It's a valuable product feedstock in chemical industry. You can find it also in deep underground with excavation, solution mining of large structures, cavities that actually allow you bring brine and get salt out of it. The huge tanks, bigger than Eiffel Tower, can be abandoned after you're done with your salt business, or they can be actually repurposed. They can be used as giant tanks that can store valuables for you in the mobile form, which we call as fluid. Now, are we doing that thing? Yes, of course. Nothing new about this business. There is a spread of salt rock across the planet Earth, and we have been exploiting this already for many years. In North America, Canada, you see, you have, in Europe we have, and there are countries that are actually blessed with this deposit in their geology. More than 2,000 salt caverns today are operational for energy purpose in North America only, around 300 in Germany only. So they are actually already part of our ecosystem already. Yeah? And why are they good? They are great seals. The lattice size distance is very, very small. And you hear a lot that hydrogen is the smallest molecule on the planet Earth, and that's true. But helium is stable in atom form, and that is smaller than hydrogen. So we've had salt caverns to seal for helium storage. So in terms of sealing property, if this is a crystal homogeneous salt, we are not too much concerned about hydrogen, because hydrogen molecule is slightly bigger, its kinetic diameter, than helium. And we have stored helium, but obviously hydrogen has chemical and biological impacts, etc. as well. You can rapidly cycle them compared to porous reservoirs. You can have in days, in weeks, you can get them. So they are like, small dogs that run quite fast and then they are big. So they are really fast workers. And so they actually deliver bigger than their capacity because you can cycle them faster. Yeah. And obviously in a dome, you can create many of them. And are they all great? No incident? I hardly can imagine any technology that we have invented with no incidents. Because we human beings learn from our mistakes, even in our daily life, let alone technology. In Netherlands in 91, there was a collapse of a salt cavern, created 4.5 meters of sinkhole, right? And Naomi's PhD is actually funded by the government to study that incident. And for us, because we need it for energy transition and our energy as well, we need to learn the most from that incident. That's the only incident that we have had. So we are studying it to say what lessons can we get from it. In Brazil, the same thing happened. You have watched in BBC, 35 caverns are going to be abandoned. Laura is sitting here, Braxham colleagues are here as well. This is also an incident. And you may not need it today. You may have decided that let's abandon them, but tomorrow you may actually pretty much need them. Salt is something that you need to know. If you have them in your geology, you need to know your home. You need to know how they behave because they are part of your ecosystem. You drill through to get pre-salt, you need to know salt. That's an essential element. Yep. So mechanics is very important. What do we do with hydrogen storage? In Teesside in UK, we have pancake-shaped salt caverns. Pancake. You extract salt, you extract hydrogen, inject hydrogen, but when you extract hydrogen, you fill them with brine, so the pressure does not drop too much, so they can structurally stay stable. If you go to Texas, near Gulf of Mexico, you see there are 3 giant caverns, cigar-shaped. I used to call it cylindrical-shaped cavern, and people in the operators' side, they were laughing at me. What is cylindrical word? It's cigar-shaped cavern. I said, fine, cigar-shaped cavern. Now it's more scientific. So say it's cigar-shaped cavern. So then it's twice of Eiffel Tower, the size of it. This is a giant one, about 1 million cubic meter of space for hydrogen. And they have been operating it in Texas cyclically. What data do we have about them? None. Why? They are worthy. When something is extremely valuable, it's not easy to get. So that's the reason. So not much public data is known about these operations. And they are very valuable operations we have been doing in decades about hydrogen. Are we doing that for energy? Yes, now we would like to do this for energy as the missing link of a scalable, low-carbon energy system. And we are doing that in the northeast of the country, in South Wending, and in Germany too. And this salt cavern there is exactly on top of Groningen gas field. It's where we have a stop producing of gas. Now above that, because the cap rock is salt for us, we are creating new caverns for hydrogen storage in the very same town that are sensitive about seismicity. So it is possible to do this right. It's just, it takes science. Not rocket science, but rock science. So, what do you consider to design? You go at the dome scale. How many caverns do I want to have? Where do I spend my asset? Big cavern or many small ones? Where do I place them? And if you want to have many of them, you may end up creating one in the not ideal location, which is near the shear zones, near interlayers, near heterogeneities. And that could have been the cause of some of these incidents, that they have not been constructed in the ideal locations. You go to one individual cavern, you need to know the structure, stability, etc., and microbiology, geochemistry associated with it, and all the way to rock mechanics of one specimen of rock salt. All of them are relevant. And when you bring them all into a framework, we have put them all in our salt cavern research theme in Delft. We call it Safe in Cave. And that's an open source simulator that does material construction calibration to the structure, and we aim to go to dome scale simulation. We are not yet there. A lot of heterogeneities, structure, mechanics, and if you want to remember one thing is geology, geometry, and geomechanics. The 3 Gs of salt cavern. And then a wise man told me, who was actually in the operation of T-side cavern, Evan Passaris, he deserves this credit, who actually mentored partly this business for me, and that he always have been telling me, geometry, geology, geomechanics. Take care of these 3 Gs for salt caverns. So the simulator we have developed open source, you can play with it, you can actually add mechanics, laws, everything. It's just so simple to do that, that just the confidentiality of this science has been mainly the matter of not being able to scale it up. So we made it all actually open access, extremely clear, and you can actually run the simulator and understand your cavern convergence, etc., as well. I'll take you to some key results for this talk. We were given a lab test by Shell. So they actually performed some lab mechanics experiment on a piece of rock salt for us, and they gave us raw data of the lab, and they said, construct your model and calibrate your parameters for this specific test. It looked like any other test for us. It was a loading, the blue curve is the axial stress, and a strain, and then all this is like loading, unloading, loading, unloading. That was the practice that happened in their laboratory. And then we said, let's zoom in. What do we see in this test? Is it just loading, unloading, and some deformation and mechanics and elasticity, plasticity, and so? So when you zoom in, you see when the blue curve, the stress is increasing during your loading, you see from A to B, the stress is increasing linearly, and the strain is also increasing. But from B to C, you see accelerated strain. The strain gets higher. It means you have actually crossed the failure. You are in the viscoplastic domain. So that's important that you know that even in this lab, you could observe that the strain rate is not constant. So you're not in a steady state creep, you are in a transient creep region. And one more thing, and that was obvious in this lab experiment much more than any other literature that we had found. Loading and unloading of this rock salt specimen was not in the same path. It was hysteretic. It did not go back and forth in the same path. And that actually was the reason that we had to construct a very comprehensive system of mechanical deformation, which covered not just elasticity, but transient creep, which is due to viscoplasticity, and then also steady state creep, which would have dislocation creep, which is very known in the rock salt mechanics, but also Some studies have discovered in 90s that when you are in low deviatoric stress regime, the creep is not exponentially proportional to the deviatoric stress. It's linearly proportional. And the theory was done before the experiments confirmed that. And that process is called pressure solution creep. And that is very essential when you do hydrogen storage, not liquid petroleum gas or gas storage, etc. So you need to have that term when you want to do hydrogen storage analysis for low deviatoric stress regimes. And then you go to viscoelasticity, which is the term that gives you this hysteretic behavior as well. And obviously, thermal strain and all the others can come. Now, imagine you have a scientific package that allows you put them all and do this research with. So you can go and now test and make learnings. Here you see the experiments with model A, B, and C. A is a model that is the most comprehensive model you have clustered. And you go to match with A, you do pretty well. But you see you're slightly different, but good. When you neglect any of these essential elements, especially viscoplasticity, you cannot match lab data at all. So it's extremely important to have these valuable lab data sets to be able to construct your model and perform. And you go to the field, you say, well, that was a rock salt like that. If I go to the seed, does it matter? The field is heterogeneous, uncertain. Why do you care too much about that viscoplasticity or that viscoelasticity, etc.? Unless you put it, you don't know your sensitivity. And you do that analysis, and you find that you may not even observe too much of impact of viscoplasticity for the field operation when you do cavern volume change, but the stress strain path or mean stress deviatoric stress path, blue and orange curves, are very different. And you can actually trigger failure if you don't model it precisely. And you come here to highlight the fact that slightly different material properties could have significant impact in the field scale. What you calibrate in the lab, and you may be already happy with your calibration, slightly deviation from that could have actually larger scale variation. What does it teach us at the end of all this practice? Field data is extremely important and extremely difficult to get. Yeah? And finally, what we call as rapid cycling. Part of it is rapidly extracting energy from the cavern because of shortage in the market, or you want to get more energy out because volumetrically hydrogen holds 3.5 less energy than methane. So if you want to extract the same amount of energy from your cavern for hydrogen, you will operate it at higher flow rates. And so you want to know, if you drop the pressure, what would happen to your cavern? This is a drop of a pressure about 8 bar per day, and these are the curves that you see from the modeling. If you increase the rate, and that's the maximum operational rate, 10 bar per day, that Dutch operators are practicing today. If you increase and increase the rate of extraction of energy from your cavern, you see something extremely interesting. You are rapidly extracting the hydrogen or gas or whatever from your cavern. You see that curve which says von Mises stresses, the deviatoric stresses over time. You see that they peak. Not only they get faster rate to increase, but also the peak of it goes higher. So you have the chance of failing the material by just increasing the rate of your operation. And it's an important topic. Rick mentioned yesterday, the day before yesterday, that when we say fast cycling, it doesn't mean that we are fastly taking hydrogen out and fastly putting it in. It's only one way when we say fast cycling. If we want to fill the cavern back, it will be slow again, because where is the hydrogen to come? They are not coming as fast rate as we want energy. But these are the curves that we get from this, just running this code. And you see the black line here. I want to highlight here the fact that these are not short-term failure curves, these black line, that you are quite operating below it and you're safe anyhow with this experiment. These are long-term failure, because salt is ductile material. And the long-term failure region is where you want to avoid crossing, and not just short-term failure region. So with that, I'd like to conclude my talk. Geometry, geology and geomechanics are very important. Rock salt business has been there before I was born, will stay longer as well. And they are our hope to be the catalyzer of hydrogen economy. And beside that, if you do the right mechanics, you will get the fact that valuable field scale data is extremely important. And if you have an incident, it's a sad tragedy, but you will get a lot of lessons from it. So that's the approach that we have. And we got a lot of lessons. So Naomi will defend in 2 years from now, and she will tell you all the lessons we have got from it. Thank you very much. And I'll be delighted to take the questions. And before, I'm sorry to stop your clapping, but this is how the code really looks like. So I brought it because of Herminio. He couldn't come here. He's going to SMRI, Solution Mine Research Institute in the US. So this is how you would actually practice in real life and run the code, and you get all the stress path, etc. It's just as simple as it looks like here to you. And thank you all the sponsors, especially Energy Simulation. Shell actually was with us for a long time, and the government as well. And the announcements are Willemijn. You have seen Willemijn van Rooyen. She's defending soon. Mongjae is defending. So they come and go, and we stay, and we age, and we see our students as young as they are always. So thank you very much, and I hope you enjoyed the talk.
Thank you, Dr. Hajibeygi. Questions?
Fantastic stuff, Hadi. I had a question from my previous life in Salt. There was a code we used when you initially did the dissolution of the cavern. It was called Win You Bro.
Oh.
You ever seen it?
No, I have.
So what do we do? What do we do now? Because those initial boundary conditions for those and things. So it was a code that I don't know. Maybe the people in Brascam will have seen it at some point. It's so as you dissolved, you could actually put in the detailed geology, the dissolution rates and stuff, and it would generate the geometry. And sometimes the geometry looked really ugly. So what's your sense of where that sits now these days for that initial boundary condition part of the problem?
Well, that's a great question, and from someone who has old hands on the topic as well. The thing is, initialization and setting up the system is not a trivial task to do, and that's clear to those who have actually done it. Creep is a long-term process that is time-dependent. You don't know what's the initial condition anyhow. I mean, you created salt is already viscoplastic fluid in slow time scale. So it's very important to say this is the time that I call it as initial condition. What we have presented here does not cover at all creation phase. And that's very important that you have noticed. It does not create that. But we do that from that operation and abandonment too. We have done a lot of analysis for abandonment. Creating the caverns can be, if you do heterogeneous, exactly as you said, you can get very, very ugly structures. And in reality, sometimes the cavern maps that we have from sonars are really complex. They have really, so is it right or not? Yeah, but great question.
Yeah, hello, Karl from Amarillo here. I have a couple questions on Safe in Cave. I was wondering which gridding is used in the simulator.
Thank you for asking this question. That's the thing that we are, one of the key factors we are different than FLAC 3D and others. We do tetrahedron, and we allow any complex geometry. That's something that Itasca does not do.
And follow-up question, do you have any models available to play with? You said the software is open source and available?
Yeah, absolutely. Yes. We had also a workshop together with Professor Leonardo earlier in Recife as well. We have a joint research collaboration together with our colleagues in Recife as well on this. Yes. So we have we have some cases. One of the caverns I show, it's a special cavern. I just am not allowed to specify the name of it, but it's a real cavern that I showed to you. It's from Germany, one of the caverns.
But are they also available to use to the public?
That data thing, it's something that is a bit outside of my expertise. If I say something wrong, it takes a long time to correct it. So I'd rather just have you talk to Naomi and others who have access to field data. Laura is here, Braxim colleagues with me.
I'll ask them. Thank you.
Okay, 2 questions online. Ali Papi says, hi, thanks for the insights. When we speak of huge intermediates, such as these caverns that can be as big as double the Eiffel Tower, how would you deal with the plume migration of hydrogen? Does this follow a porous medium model, or do you need to
No.
develop new models that can follow Navier-Stokes equations?
No, this is a tank. We have insolubles in the bottom. By the way, glad to hear from you, Ali. And so you have a tank. On the bottom is mud, insolubles, mineral rich, above which you have brine, and then it's a tank. You put some cushion gas and then hydrogen or methane or whatever you want. Cushion gas maintains the structural stability. And so you have no such a thing as migration of plume or porous system,
like
unless interlayers that cross your caverns are porous. They are tight, shale, but scientifically, hydrogen can penetrate through them, and that would be just penetration of hydrogen through these interlayers, not more.
Okay, second question from Hassan Gorgon-T. He asked, what is the scale of injection rate and production rate for depleted gas reservoir to store hydrogen, and what about salt caverns?
Well, if you ask it as if we are doing it for many, many sites on the planet, no. We have only one site in Austria, which is storing pure hydrogen, and is only for research, 1 million cubic meter. The plan is seasonal for porous reservoirs. For depleted reservoirs, we are talking about feeding them in summer. In wintertime, we take it out. That's the scale. For salt caverns, it can be very much. It can be non-linear. It can be weekly, daily based, etc. And they are the catalyzers for enabling hard-to-abate technology economies like cements and others easily rely on a feedstock and baseline of hydrogen supply to them.
Okay.
So you can have on daily basis as well.
Yeah. Any questions?
Professor.
Yeah, Nada.
What about salt mines, not salt caverns? It's possible?
If you seal them, well, I asked this question of possibility to a wise colleague from Halliburton. He said, if you buy it, I make it. I don't see it at this moment, any scope of any more of those kind of open mine, but it might be possible because you could be able to see how thick they are and if you can really make something there. But the sealing would be most likely. That's if you most likely know more.
Yeah, it's interesting because sometimes, many times, the salt mines are monitored, so we have data from the formations and
exactly.
the history.
That's right.
It would be interesting.
I said something very briefly. I said developing them in non-ideal condition, and I also meant places that might be even tectonically active, and that they have salt as well, and they are actually right now exploring in the Middle East to see whether they can make salt caverns for it as well. Okay. So non-ideal cases are exactly when engineering really makes a lot of difference.
Okay.
And for that incident that in Hengelo happened also, we know that this was close to also shear zones, and we know that the roof was not thick enough. So we have taken as much lesson as we can avoid in the future as well.
Exactly.
But that thing, maybe I said it twice already, but it's really great opportunity to look into an incident and try to really accept you did wrong and then take the most possible lesson and do better tomorrow. Whether your own life, we do mistakes a lot, and whether it is on salt cavern as well. Take your mistake and do better tomorrow.
Great. Thank you, Hadi.
Of course, my pleasure.
Thank you, Professor. Outstanding talk. I have a quick question about the salt rock typing. Is something relevant to consider the salt stratigraphy for the salt cavern design, or I can consider like a homogeneous salt?
Excellent question. Absolutely, yes. Especially now we are at the development of clusters of caverns for hydrogen or whatever else. It's extremely essential to monitor them, and especially the baseline monitoring before we go and drill and do anything. To know what was already the activity before we come. Before we came, it was already an active area. And that's very important to know that what else have we done to it to disturb it. We have done recently that type of thing. When I say we, means that I'm speaking about it. A lot of other colleagues did it, with also colleagues from University of Oxford, to get seismicity map of the North Sea for all the operations that we do. And it's already a big, giant type of noisy area. And it's important when we start Porthos next year to know that how much addition of these activities was due to Porthos. But the structural analysis, heterogeneity, and covering the fact that where are the ideal locations for you? Can you do that in the ideal location? I think yes. If you want more, then you go non-ideal, but Even a strategic petroleum reserve of the US, also they are also having some interlayers and shale layers, etc., but they have been working on it for many years. When you know your geology, you know how to deal with it. But it's important to know your geology. You can't just say, there was an incident I abandoned. I need to know my home. I need to know my geology, irrespective of whether this is for the application or the other. So salt is an essential thing to just know about. Yeah, excellent.
Question, Hadi. In the name of research, safe in cave, what other technology gaps or research areas you need to strengthen and make it more robust?
Well, there are some technical side for it. We do implicit integration because I am reservoir engineer. We come from reservoir engineering. I mean, I was summer intern at Chevron San Ramon in Intersect, etc. So we know reservoir simulators, and we have developed those as well. We come from that community to salt cavern community. So there are some stability analysis, implicit time integration, mesh flexibility, etc. We have brought them all here. This is the only one that works with tetrahedron. And mathematically, you can prove that they have oscillations, and we have fixed that too. So we are writing papers about it. Viscoplasticity is not an easy thing to do. It also works here. We have implicit viscoplasticity, transient creep, etc. But these are just technicalities we can discuss with our colleagues at FLAC 3D and others. The reality, the real value of this is that it's meant for students, for research, for education. It's meant to be simple, understandable. I've had operator colleagues in our short courses on the topic. After leaving, they say, we didn't know it was so simple, even the viscoplasticity behavior of it, etc. So I think this is disclosing the science and scaling it up to say it's not rocket science, it's just rock science. That's
okay. Thank you. It's 10:15. We should thank you again for your presentation.
Thank you. Thank you.